Question 1 is we need to analyze the equilibrium of the tower crane. First, we look at the sketch of the crane, and we can see they consist of the two beam and two supports, which is some load applied on it. I marked the beam of the crane in purple and red color to help me to presentation the load. So we first look at the purple beam, and there's three load applied on the purple beam. One is the building material hanging on the end of the purple beam, which is 10 kilonewton, and the wing load applied on the beam also, they're 5 kilonewtons. And FW2 is the weight of the beam itself, is 24 kilonewton, and the beam is 10 degrees above the horizontal level. And let's go to the red beam. The red beam itself weighs 16 kilonewtons, and the operator rope is a load added on the red beam, which is 7 kilometer, and the concrete block is weight 20 kilometer applied on the end of the red beam. Okay, let's take a look of the support on the crane. The crane has two support. One is the support A, one support B. The support A is a pin support, and there are two rejection force on pin support A, without a vertical rejection force, and another one is the R-A is a horizontal rejection force, which is weighs 3.83 kilonewton, and the vertical one is 34.35 kilonewton. Let's go to the roller support B, and there's only a RB vertical rejection force. It is 45.86 kilonewton. Okay, in order to check the equilibrium state of the crane, we should take moments about point A and point B first, and check whether the sum of the moments on point A and point B are equal to 0. Then we should calculate the sum of the vertical force of the crane to see whether it is 0 too. And the last step is to calculate the horizontal force to check whether they are 0 also. And if those four steps is all equal to 0, then we can make a conclusion the crane is under equilibrium state. Okay, so let's take a close look of the equation. Let's look at the sum of the moment and taking on point J, and we assume the crosswise moment is all the positive. The anti-clockwise moment is all the negative. So the sum of moment on point A is 0. Same method, we take the moment about point B, and then we calculate also 0 too. Okay, next let's go to the sum of the vertical force, and we assume the downward force is all positive, the upward is negative, and we calculate is 0 also. Last, we go to the sum of the horizontal force. There are only two horizontal force on the whole crane. One is F-2, which is the wind load, and another is the horizontal rejection A, is the R-A, which is in this position. And then we calculate also the 0. And based on those four steps is equal to 0, we can make a conclusion that the whole crane is under the equilibrium.
I'm LUN. In this project, I'm responsible to the question number 2, analyze its thrust, deformation, and buckling of its members and equilibrium. And in this question, I'm going to study a footbridge nearby my home, and this is a footbridge in CHEUNG. And according to the structure of this footbridge, I draw a picture like this, and you can see this. There's two support, just like the picture, and here one is a support B, and here is support A. And then I assume all the members in the structure is in the same length. They are all 2 meters. And also add some data into this structure. For example, 5 kN of horizontal wind load and 10 kN of horizontal wind load from the other direction. And here I assume that about 2 to 3 people standing at this point, so you have a 5 km of point node, and also and here also, and this 10 km of loading is the weight of the footbridge itself. And okay, let us go to our calculation. Um, in the to start the calculation, I start the calculation at the support. You can see that I take moment at point A first, and sum of moment about A equal to 0. This is 2 times 5. This is a clockwise moment at point A. 6 times 10. This is also another clockwise moment at point A. 10 times 5. And cosine 30 times 2 times 5. How come cosine 30 times 2? This is a horizontal distance between the wind node and the support A, and it's just simply use the 2 meters times the cosine 30. How come 30? It's because the right angle and minus this and minus the 60 degree, and it's 30 degree here. And then the and then we can see the right hand side of this equation is the anti-clockwise movement and 10 km because it's the same distance with this window, so just cosine 30 times 2 again and times 10, and also plus 12 times b is the reaction force of the support b. And then finally we can find out the reaction force of the support b, and then we can use sum of Fy equals 0 to find the reaction force of the support A. And then because support A is a pin support, so this have a horizontal reaction force also. So we can use the sum of Fx equals 0 to find the horizontal reaction force of point of support A. Okay, after finding the reaction force of two support, we can start to analyze the truss. And I use two different methods to analyze the truss. One is method of join, and other one is method of section. We look at method of join first. In method of join, there are two unknown, and it is acceptable because two unknown, two equation. And we can look at sum of Fy equals 0 first. In this situation, AE need to change it to the vertical force. So we need to AE times cosine 13 to change it to vertical force, and then put it into sum of Fy, and you can find out the value of AE. And put AE into sum of Fx, but you need to change AE to the horizontal force first, and then you can find the value of AF. Okay, let us look at method of section. In this situation, I will focus on the left hand side of the section because the number of force is lesser than the right hand side, so that the calculation will be faster. And first, we need to use sum of Fy equals 0, and you need to change AE to the vertical force first, and then you can find out the value of AE, and you need to take moment at point E to calculate the AF. And here is a 2 times cosine 13, and it is a horizontal distance between moment E and AF. And then put the value into the equation, and you can find out the value of AF. Okay, let us look at join E. Join E is the same procedure with the previous calculation. It's just sum of Fx equals 0 and sum of Fy equals 0. The method of section also same procedure. Sum of Fy equals 0 and sum of moment at a point. To be honest, this is just repeating the same procedure and putting different value, but this really spent me a lot of time because I did two methods. And maybe method of section have a little bit different after the midpoint, because after midpoint the number of load at right hand side is lesser than the number of load of left hand side. So after midpoint, I will focus on the right hand side. And then just repeating the same procedure and until the last session, and the last join. At the last join, because we have the value from the previous calculation, and here is the force from in this situation. If I put both data into one equation, and the result is the left hand side equal to the right hand side, that means there is no mistake in previous calculation, maybe. And at the end, I list out all the members of the footbridge, list out how many force in each members and what force they have in each member, compression or tension. And this is the end of the analyzing truss, and let us go to the deformation of truss. The second part of the question number 2 is to calculate the deformation of its member. To calculate the deformation of each member, we need to know the shape of the members and also the Poisson ratio and the Young modulus. As you can see it in the picture, the member is rolled and assume the material is steel. And I draw a cross section of rod over here and assume that the dimension of the rod is 0.6 meter and the length of the rod is 2 meters. And we can see that the Poisson ratio of the steel is 0.27 to 0.3, and it is derived from wiki. And let's say 0.3 first. And the Young modulus of steel is 200 GPa, and 200 GPa is equal to 2 times 10 to the power of 8 km per meter square. And this data, we can put it into the formula, these two formula. This formula, one is calculate the change in length, and another one is to calculate the change in diameter. Let's talk about the formula of change in length first. Is the force times the length, the original length, divided by the Young modulus of steel times the area. We can see that below 1.19 is the force. I put it here and times to the original length of the members and divided by the 2 times 10 to the power of 8. It is the Young modulus of steel times the 0.09 pi. This is the area of the rod. You can use the 0.6 meter diameter to calculate this area. And let us talk about the change in diameter. The formula of change in diameter is about the Poisson ratio. The Poisson ratio is equal to epsilon y divided by epsilon x. After changing the position, the formula will become the change in length in diameter equal to the Poisson ratio times the epsilon x times original diameter, and epsilon x is equal to the change in length divided by the original length, and you just put the value into this formula and you can find the change in length and diameter. And this table is the members that under compression, the change in length and the change in diameter. This table is the members that change in length and change in diameter under tension. And you can see if the members that under tension, the result of change in length, that means the member will be increased about 1.38 times 10 to the power of -6 over pi meter. And if this is change in diameter under tension, and that means the diameter will be smaller. And if this is the change in length under compression, and that means the length will be decreased about 1.32 times 10 to the power of -7 over pi meter. And if this is change in length, it is change in diameter under compression, and that means the diameter will be increased. After the calculation of the deformation of all the members in footbridge, and then we can start to calculate the total change in length in the footbridge. And I divided the footbridge into 3 different parts. One is bottom part, and upper part and the middle part. First, we look at the bottom part first. And we can look at bottom parts, and there are AF member, FH, HJ, JL, LN, and MB, and add them all together, and they are all compression, and then the result is 2.33 times 10 to the power of negative 6 meter. That means the bottom part will be shortened about 2.33 times 10 to the power of negative 6 meter. And then we can look at the upper part of the footbridge, and at the upper part of footbridge there are EG, GI, IK, KM, and NO, and they are all tension. And after calculation, and the there are four, and the change in length is 4.186 times 10 to the power of negative 6 meter, and in tension that means it will increase at about 4.186 times 10 to the power of negative 6 meter. We can finally we can look at the middle part of the footbridge, and half of the middle part of the footbridge is in tension and half of them are in compression. And we can see that the value of compression and tension is equal. That means there is no change in the length of the middle part of the footbridge. And then this is the end of the analyzing the deformation of the footbridge. And then let's go to the buckling of the footbridge. The third part of question number 2 is to analyze the buckling of its member. And in this part, I will only analyze the bottom part of the footbridge. And you can see that just like the picture of the right hand side, I draw it out, and it is a rock, it is steel rod, and the length of this steel rod is 12 meters, and the cross section of the rod is about with the 0.6 meter diameter. Then let us go to the K value. Before the calculation, we need to find a K value first. You can see that this steel rod is with one end with pin support, another end with roller support, just like the right hand side this photo, roller support and pin support, and the K value is 2.0. And now we can start our calculation. At the calculation, I'm going to determine the critical Euler load, and that means PCR. First, we need to know what is I. I is the second moment area of the circle, then the rod, and then you just put the diameter of the rod into this formula, and then you will come out the result. And then LE is the K times the length of the rod, and you will come out the result, and just put these two things into the PCR. And also the E is the Young modulus, and you need to change 200 GPa to the 200,000 MPa first, and put this three value into PCR, and then the critical Euler load will come out. This is the end of the analyzing buckling of its member, and this is also the end of the question number 2. Thank you.
State. Question 3, we need to analyze the bending moment, shear force, and stress on the beam. So we select this situation to analysis. We analyze the beam marked in red line. So there is a point load applied on the beam, which is 7 kilonewton, and there is a UDL applied on the beam. There's 1 kilonewton per meter, and there's also a point moment applied on the beam, which is 15 kilonewton meter. And according to those three information, we can calculate the restriction force on both ends of the beam. So after we got all the information, we can calculate the shear force from the left to the right by section. So this is the section analysis. We calculate the shear force first. According to the sum of the vertical force is equal to 0, we can easily calculate the shear force by section, just like this and this. After we obtain the shear force, we can plot the shear force diagram just like showing in the picture, and we should pay attention to the shear force is equal to 0 because there is a maximum bending moment in this position. Just like the shear force calculation, we also calculate the maximum bending moment from the left to the right bisectionally, and by the equation of sum of the moment in each section is equal to 0, we can calculate the bending moments in each section. Just like this, this. So after we obtain all the bending moment in each section, we can also plot the bending moment diagram. And there is a parabola in this position because there is a UD arrow applied on the beam, and the straight line indicates that there is a point moment on the beam also. And according to the similar triangle, we should calculate the maximum bending moment in this position by the equation of this. And plot the maximum bending moment on the top of the parabola. We are curious to know what is the bending stress on the beam under the maximum bending moment. So we decide to calculate the magnitude of the bending moment in the beam under the maximum bending moment. In that position, the beam is under sagging. That means there is a compressive force on top and there's tension force on the bottom, and the beam is also bending above the x-axis. So in order to calculate the bending stress, we should calculate the second moment of area of the cross section of the beam first, and based on this equation, and we calculate the second moment of area. Then we obtain the maximum bending moment according to the diagram, and we input in this formula. Then we got the maximum bending stress of the beam.
The next question is about analysis of the column under eccentric loads in AC3, and we need the equation to help us calculate the stress of the column under the eccentric loading, which is P over A is the direct stress, and the M over EZ is the bending stress. To use this equation, we need to know about what is the meaning of each symbols. The sigma O is the direct stress, the sigma B is the bending stress, the P is the applied load, D is the diameter of the circular column, A is the cross-sectional area of the column, M is the bending moment acting on column, E is the eccentricity, I is the second moment of the section, Y mass is the mass centroidal distance, which is the diameter over 2. EZ is the section modulus, which is the second moment over the Y mass. The question is, a circular concrete short column is shown in this picture. If P is 200 kN and E is 25 mm, determine the stresses at all corners of the section. First, we need to calculate the bending moment acting on the column, which is the P times E equals to 200 times 0.0025 equal to 5 kNm, and then calculate the second moment, which is pi times d to the power of 4 over 64, which is the pi times 200 to the power of 4 over the 64 equals to 78.5 times 6 orders of magnitudes, mm to the power of 4. Then we need to calculate the Z, which is I over Y mass equal to 7x 7x.5 times 6 orders of magnitudes over 100 equal to 7x5.4 times 4 times 3 orders of the magnitude cube. So we can use this value to help us calculate the direct stress and the bending stress. Then we need to calculate the sigma mass, which is the direct stress plus the bending stress, which is 200 times 3 orders of the magnitude over pi times 100 squared plus 5 times 6 orders of the magnitude over 785.4 times 3 orders of the magnitude equal to 6.37 plus 6.37 equal to 12.74 MPa, and the value is positive, which is the compression, and the sigma minimum is the direct stress minus the bending stress, which is 6.37 minus 6.37 equals to 0. That is the tension acting on the section which is no tension acting on it. Is because to avoid the failure of the column due to the eccentric loading, there should be no tension acting on the section, and the load is applied on the front side of the column, so the compressive stress is acting on the front side. So the sigma of A and B is equals to 12.74 MPa, and for the back side of the column is the tensile stress acting on the column. So the sigma of C and D is 0.